When you put water on to boil, you might notice that the pan gets hotter faster than the water does. Since the burner, the pan, and the water are all in contact, heat is being transferred from the hot burner to the pan and then to the water, but their temperature doesn't go up at the same rate. Even if we controlled for the mass of all three items, their temperatures would still rise at different rates due to an inherent material property called heat capacity. Heat capacity is the amount of energy a material has to absorb for its temperature to rise by 1 degree, or the energy that it has to release in order to drop by 1 degree. Formally, it's written as du over dt and has units in joules per Kelvin. Because the total energy contained in a system is also a function of the amount of material, we usually see it written as the molar heat capacity, or joules per mole Kelvin, or the specific heat capacity, joules per kilogram Kelvin. With a little algebra, we can rearrange these equations into the change in internal energy equals the number of moles times the heat capacity times the temperature, and for specific heat capacity, the change in internal energy is the mass times the specific heat capacity times temperature. Now, for these to be true, all the energy we're adding to the system has to stay in the system. So if we transfer the energy as heat, we have to define the system so that no energy is being released back into the surroundings through work. In other words, where the internal energy is equal to heat times work, work has to equal 0. And for this to be true, volume has to remain constant, since work is also equal to the negative external pressure times the change in volume. If there's no change in volume, there's no work. Therefore, we've defined the heat capacity at a constant volume, and a definition for the internal energy of a system, U equals moles times the heat capacity at a constant volume times temperature. And this relationship remains true whether we're doing an experiment at constant volume or at constant pressure. It hasn't come up yet, but keep this in mind for the future. So what if we have to do a reaction in an open container under constant pressure conditions for reasons of safety or practicality? Some of the energy will return to the surroundings through work, but how much? For solids and liquids, the change in volume per change in temperature is usually negligible. So for the purposes of this course, the heat capacity under constant pressure, Cp, for solids and liquids is equal to the heat capacity under constant volume. For gases, it's a different story. As we've seen, the volume of a gas is very sensitive to temperature, and so much more of the heat gained by the system is immediately lost back into the surroundings as work. We have a way to calculate how much is lost to work by using the ideal gas law. We've seen that the internal energy is equal to moles times the heat capacity at a constant volume times temperature, and the internal energy is also equal to heat plus work. Q at constant pressure is what we've defined as enthalpy, H, and work is equal to pressure times volume. So moles times the heat capacity at a constant volume times the temperature is equal to enthalpy minus pressure times volume. And according to the ideal gas law, PV equals nRT, so enthalpy equals nCVT plus nRT, or the moles times the heat capacity at a constant volume plus R multiplied by the temperature. Therefore, under constant pressure conditions, what we're really measuring is the change in enthalpy, and the heat capacity under constant pressure of an ideal gas is the heat capacity under constant volume plus R. We'll go into more detail about the heat capacities at constant volume and constant pressure of ideal gases in the next video.